coordinate system. So the three coordinate systems that we can jog in. Now this is jogging. This is not programming. This is jogging. Y'all understand that? We can do what we call a joint jog. Then we can do what we call a world jog, which we call it the world coordinate system. And then we have what we call a tool coordinate system. And then we have what we call a user coordinate system. And we're not playing around with the user coordinates because what is the user coordinates? Anybody remember?
Coordinates that only be used as operating.
It's a good guess, that's not right. No. A user coordinate. So what do we mean by a coordinate system? Well, we jog within what we have two basic categories. We have what we call a joint jog, and then we have Cartesian jogs. So we have one jog that does not jog within a Cartesian system, and we call this the joint coordinate system. So who controls of course the controller controls the axis, but who determines which axis moves on a joint? You do, right? You understand. You determine that. Everybody understand that? And this is the only coordinate system that you determine what axes are going to move. Once you switch over to a Cartesian system, the controller determines which axis that will move to make it jog within a Cartesian system. And what's a Cartesian system? Huh?
Rectangle.
Yeah, rectangular, X, Y, Z, roll, pitch, yaw. Everybody understand that? Roll, pitch, yaw. X, Y, Z, we call it the right-hand rule of robotics, right? Now understand, this is not the Cartesian system. This identifies the direction the robot will move within the Cartesian system. A lot of people think that this is the Cartesian system. This is not. The Cartesian system was developed in about 1837. How many robots did we have in 1837? None. So the Cartesian system has been around for centuries, right? You understand that. And what it does, it specifies a place in space using X, Y, Z. And then roll, pitch, yaw came along with robotics, okay? So the joint coordinate system is not a Cartesian system. So then we got the world Cartesian system. Well, the world Cartesian system is Cartesian relative to the center of the base of the robot. Everybody understand that? And all these robots in here jog X, Y, Z. They jog exactly the same if we have what we call the world coordinate system selected. And you're supposed to be reading this, right? This is going to be on the test today. A lot of this is going to be on the test today. I hope y'all study for it. Y'all know we have a test at the end of class. Then we have what we call the tool coordinate. This is Cartesian relative to the what? To the tool. But it's still X, Y, Z. It's still X, Y, Z, roll, pitch, yaw. And then we have user coordinates. User coordinates it gives you the ability to establish X, Y, Z. What direction do you want it to go? Y'all understand that? Everybody okay? So this is a user configurable frame, and this is a user configurable frame too, and we'll look at that. So there's two things that we're going to do is we're going to teach what we call a tool frame. So what we'll be able to do is during a tool frame, we're going to specify the location of the tool center point. And then a user frame, we'll do one of those. And what we'll do is establish the direction of X, Y, Z. And this explains frames. Now the three moves we have on all these robots, some of them have more, but none of them have any less, is we have what we call a joint move. which has nothing to do with a joint jog. And this is the problem we have. One of them is a program instruction. The other one is the way you move the robot, right? Manually. And people get these confused with each other. They are not the same. Okay. I mean, this is what I was looking at yesterday. Programming basics. Thursday. Programming basics. We looked at basically, we talked about a command, an instruction. What's the three parts of every instruction? Well, most instruction, there's actually two required parts, and one of them is optional. What's the required parts? First of all, we get a what? Line number. Then after the line number, we're going to have a what? Command. And then after the command, we're going to have information that's required by the command. Now that's what's optional. So some commands, like if I say stop, there's nothing but stop, right? You understand? But when I'm driving, so I'm stop at a red light or a stop sign, that's a stop. But when I'm driving, there's certain things that we have to look at, right? You understand? We have to make sure we're going in the right direction, and we have to make sure we're going in at the right speed. So the speed is not required by stop, right? You understand that? But the speed would be required when we're in motion. So the main parts of an instruction is a line number, followed by the what, followed by the command, followed by the information required by the command, if required. So this is an example of a move instruction for the FANUC robot. And this is the FANUC, this is all the FANUCs we have in here. First of all, what's this number right here? Line number. What is this? J means that's the command. It's not a label, it's a command. And why we're going to correct you on that is we do have what we call labels, which has nothing to do with this. So this is the command right here. That little old J right there, that's a command. And that means this is going to be a joint move. The P1, that's the point number. That's optional. That won't be required. That's required for this command, but it's not. I'm sorry, for this instruction, but it might not be required by the next one. Does that make sense? This determines the speed of the move. We're going to move this at 100%, and then this is going to be the amount of round off, which we're going to talk about here in a second. So this is the basic layout of an instruction. Right? And every one of them is basically the same. Motorman calls theirs move J, M-O-V-J. And that would be a move joint instruction. They call the velocity VJ for joint moves. And then we have what we call the round off, which is optional. And then the KUKA calls it PTP. That's their joint move. Followed by a percent speed, followed by a round off, which we'll look at today. But they all follow the basic syntax for an instruction. Now, in computers, what is syntax? That's YNTAX. We talked about that last class too. What is syntax?
The correct way of writing.
Good. Y'all hear Patrick? It's the correct way of writing in a language. In computers, syntax has to be perfect, right? Y'all understand that? So they understand that. So what they're going to do is that when you want to do a joint move, you're going to select the move from a menu. You'll say joint move, and then when you enter it, it'll pop this instruction into your program with the right syntax. But the problem is that this stuff has to be included. So what's it going to do? It's automatically going to stick some values in there. It may not be the values you want, but it's got to be part of the syntax, right? You understand? So we call those defaults. So a default is what a computer uses if you don't tell it what to use. And these defaults have got to be there. Y'all understand? What FANUC does is it uses the last instruction as your default. So if you make the corrections in this instruction, the next time you use a joint move, it will stick the last thing you used. Does that make sense? So we have a joint move. A joint move is an uncontrolled path move, which means the path it takes is not guaranteed. Y'all understand that? But this is the fastest the robot, we can actually move the robot using a joint move. In the other class, we talked about when you try to move extremely fast with your hand, it's impossible for you to do it in a straight line. Because as soon as we say move your hand in a perfectly straight line, then you're going to have to slow down. So anytime we use a control path move, we specify the speed, and the speed is going to be maximum. Joint move will run the robot as fast as it can move. But the path is not guaranteed, so we call this an uncontrolled path move. Normally we use a joint move to get it from its start position down to the workplace. Try to get it down there as fast as we possibly can, right? And then sometimes even when we're moving from different points that we want to teach, it depends. One of the things that we're looking for on a robot is to do things extremely accurate and as fast as we possibly can do it. If a human could do it faster, they would use a what? They could use a human. You already don't understand that. If a robot can do it faster, then they'll try to use a robot. And that's what's happening, especially on repeated paths. Everybody okay on the makeup of an instruction? Talked about that last class. So here they show a joint move between point 1 and point 2, and notice they show it moving in an arc. And that's pretty common. We'll show y'all some of the stuff over there. Everybody okay? Any questions here? Now the other move that every one of these robots supports is what we call a linear move. Linear move means it's going to move in a what? Straight line. So linear move causes the robot's tool center point to move in a straight line from the previously taught point. It is a controlled path move. So now the robot is not just turning on all the axes at the same speed. So a joint move, what makes it move in arcs and all kinds of stuff is that it turns all the axes on at the same speed. So that means some of your axes are going to get to their final point before other axes. So that means the thing is going to move in an S or an arc or some pattern, right? You understand, but it's not controlled. Here, what's going to happen is we're going to specify the speed of the move. Timon, you texting back here or doing something in class? Timon. It's obvious that you're not paying any attention. I hope you do okay on the test today. I hope y'all pay attention to the, we had a couple people, had an assignment due that was due Friday. Some of y'all hadn't done that. You're supposed to send me email that was in the assignment, so I got some of those from some of y'all. You need to check your course calendar. None of y'all signed up for that texting application, which I would be more than glad to send you a text saying, you know, you have an assignment due, just to remind y'all. If you're not going to sign up for it, then it's up to you to keep a monitor of that calendar, right? You'll understand that, and get those assignments when they come out. So if you did it and sent me an email, you're okay. If you didn't, then you've lost 30 points already from a 50-point assignment. So you can get 20 points if you do it, and 20 points is better than none, right? So it's 10 points for every day that the assignment's past due, and it was due Friday at midnight. So that was Friday, Saturday, and Sunday. Saturday, Sunday, and Monday. So if you're not going to sign up for that remind, that's fine. Nobody in this class did it. It's extra work on me. You know, I would be glad to go back and text y'all saying, okay, this assignment's due and that kind of stuff. I don't get your phone number, even though every one of y'all hopefully gave me y'all's phone number in Blackboard. But that's a really good feature that, and it don't cost a dime. It's a free application. You don't have to even do that. You can, I think it's 801. It's a text you can send, and I can respond to your text. But if you want to get automatic text from about the college, then you need to sign up for it. The procedure is located in the course content. Should be right around the top for signing up for that. So, huh? Yeah, that's what it is. That's what was, because a lot of people have a problem checking their email, and I understand that. So a linear move, we move in a what? Yeah, this is a move instruction. This is not a jog. This is a move instruction, which we tell the tool center point to move in a straight line. This one from the previously taught point. Y'all understand that? So I might use a joint move for my first instruction, and then it'll stop at that point maybe. We'll talk about that in a minute. And then I'll use a linear move as my next instruction. Well, from the previously taught point, it'll move, the robot will move in a straight line. Now this is programming. This is not jogging. Y'all understand that? I mean, if all I had to do was jog a robot, and that's the only way I could move the robot, then I definitely wouldn't buy a robot, because you'd have to have somebody. So Mercedes has got almost 1,300 robots down there. And those robots are running programs, right? You understand? 99.9% of the time they're running programs. We jog it when we teach it. We jog it to clear it. We jog it and put it in manual mode every once in a while. But there's odds are you got probably maybe not many people in that whole robot section down there, right? So they just sit there and run automatic. So what they're going to do is they're going to run a program. So the linear move instruction, this is for the motor man, and there they are, right? I left out the lineman. Remember, that's what it says. MOVL, which would probably indicate a what? Move linear. What's V equals 50? That's the speed, and that's 50 millimeters per second. And then this out here is what we call the round off, which we need to understand. So this is going to get that spot perfectly. Now the last move that all these robots support is what we call a circular move. It says the circular move instruction causes the robot to move in an arc that passes through 3 points. And who defines the 3 points? You're the programmer, right? You define the 3 points. So we have a start point, which they're calling point 1 here. Then we have an intermediate point, which is along the arc, and then we have an end point. And they call it circular. I'm sorry, it don't make a circle, it makes an arc, but they refer to it as a circular move. So if I wanted it to do a circle, then I would have to do 2 circular move instructions. Because about the best we can do with an arc is 180 degrees. And then we would put another circular move instruction to make it finish the circle. Now, by the way, how it comes into the arc depends on the robot. The motor man requires you to teach all 3 points. No matter how you enter this point, you have to duplicate it as a circular move. All the other robots, you come into point 1 using some other move, like a linear move or a joint moves. And then you teach two additional points. But no matter how you come into P1, there's 3 points required in a circular move instruction. And this is a circular move instruction for the FANUC robot. So we're calling, the points are numbered 5, 6, and 7. There's your 3 points that's required for the circle. On the FANUC robot, we come in with a J, that's joint, a P5, and we teach it using what we call a fine round off, which we'll talk about in a minute. And then the circular move consists of the other 2 points, and you have to teach a what? An intermediate point and a end point. And you have to specify the speed in units. So this would be what? 50 millimeters per second. 500, I'm sorry. I got my glasses. Okay, so here's what we're at today. This is round off. Now the problem is we've only got 3 move instructions. So the problem we have is with 3 move instructions, it looks like we would be very limited on what we could teach the robot to do. So let's say I wanted to make it follow this path right here. How could we do that? Well, using 3 move instructions, it's going to be basically impossible, right? Does that make sense? So what we do is we have the ability to tell the robot to cut corners. So it's just like a lot of us do when we drive. It's awful, people come, they're in the right-hand lane and they make a left-hand turn and they cut the corner so much they come over in your lane. You know, you're pulling up there, they come over in your lane because they cut the corners. So they don't want to do what? So if you wanted to make a 90-degree turn, of course you can't hardly do that with a car, but what would you have to do? You would have to stop, turn your wheels, and then turn, right? Don't understand that. If I was going to make a 90-degree turn. Well, most of the time we don't do that because it's not necessarily. We slow down a little bit and then we do what? We cut the corner. But what it does is it provides us the ability to take different paths, right? You understand that? So I can follow a cut. Instead of me following a curvy line using linear moves and circular moves, we cut corners while we're driving all the time. That makes sense. What we do in robotics, that corner cutting, we refer to that as round off. Every move instruction must also indicate if the robot is to stop at each top point or continue through the point without stopping when the tool center point changes direction. This feature is given a different name for every robot in the lab. The KUKA calls it continuous. ABB calls it a zone. Motorman calls it a position level. And then FANUC calls it fine and continuous. Y'all understand? And so that's why we're going to call this round off. Round off is a method used by programmers to tell the controller how the robot is to cut corners when moving through a point that changes the robot's direction. And this is the Motorman robot. Motorman uses what they refer to as a position level. So these are points, this is point 1, this is point 2, and this is point 3. If we specify a position level of 0, it will hit the point. So what does that mean? That means the robot is going to have to stop. It's going to have to decelerate, stop at the point, and do what? Change directions and accelerate out of the point. It's kind of like you trying to make a 90-degree turn, which sometimes it's required, sometimes it's not. Does everybody understand that? If I use a position level of 1, then it would cut that corner right here. 2 would do this, 3 would do that, 4 would do that, 5, 6, and 7. We have 7 position levels that's available to us. Does that make sense? So what we could literally do to make it follow any path we want it to follow, whether it's a straight line or whether it's a circle or whatever, what we could do is we could just specify, we could do a linear move or a circular move or whatever, and then specify a round off. Does that make sense? So let's change this up a little bit to make it look a little better. So let's say I wanted it to come up to here and then do this. Well, what I could do is I could teach this right here as a linear move, and then I could come over here and teach a point out here somewhere, and then I could teach a point down here, and then specify what? Specify a round off. And so what the robot would do, instead of coming out here and hitting this corner and then coming down, it would do what? It would literally cut the corner. So using those 3 moves and then round offs, we can make the robot follow any path we want it to follow. Do y'all understand? So the last thing of all these instructions is a round off. So FANUC calls it continuous. So if I say continuous 100, this is going to be the maximum round off. Oops. The Motorman, if I specify a position level equal to 7, then this will be the maximum round off. So on the FANUC, this is your 2 options. You can put continuous and then you specify the amount of round off, or you can put fine, and this right here will do what? It will do what? Hit the point. So FANUC calls theirs continuous and fine. If you specify a continuous move, you specify the percent round off. If you specify a fine move, the robot will hit the point. On the Motorman, if you say position level equal to 0, then this will do what? This will hit the point. On the KUKA, which none of y'all are using, if you don't specify a continuous move, it will hit the point. Yeah, so FANUC has continuous and fine. KUKA has continuous. So if you wanted to round off, you would add continuous to the instruction. If you leave it off, it will be a what? It will be a fine move. ABB calls it a zone, so it's kind of like a position level, but they call it a zone. If you specify a zone of 0, it will hit the point. And the bigger the zone, the more it will do what? The more it will round off. And some of y'all are on the ABB. So when you insert an instruction into a program, it's either going to come up with a round off or it's going to be something you have to stick on there, right? You understand? So round off is optional on all these robots, except the FANUC. The FANUC, you either specify continuous or fine. If you don't specify a position level on the Motoman, it will round off depending on, it will automatically round off depending on the speed, which is nice enough. So that means if you want it to hit the point, the midpoint, you have to put a position level 0 in there. If you want to control the round off, you have to put a position level in there. Does that make sense? So even though it appears like we have limited capabilities with just 3 moves, we can make this thing follow any path by figuring out which move to use and then figuring out what, how much round off to add. Now this is where it comes difference when we start running the program. So we got, wait, and we need to make sure we understand this because some of y'all are fixing to start. So these are some instructions, move instructions, joint, linear, and circular. Do y'all have any questions on that? This is Motoman. I'm sorry I didn't put the Cook. I should go back. But they basically are laid out in the same format, right? Running the talk program, we can run it in what we call the teach mode. So what's the 3 modes we can put the controller in? 2, all of them support 2. Teach and play are automatic, right? And some of them support what we call a remote, which we talked a little bit about that. But these are guaranteed. So these will be the ones that we're going to play around with. So we have teach single step, we have teach run. And some of the robots support what they refer to as a high-speed teach. This is where you can run the program. Automatic mode, we have 2. We have what we call play, we're going to call play single step and play run. So what do I mean by single step? But we're doing a program, but what do you think it's going to do? It's going to do 1 instruction per time, per sequence. So on these, you got to constantly press a button, right? You understand that. It'll do 1 instruction, and what will you probably have to do? You'll probably have to release the button and press it again. We use this to verify, basically to verify points. It does not verify the path the robot will follow when you run the program. We do this to verify points on robotics. When we got the Amatro line, the Festo line, you don't have, the only way you can single step the Festo line is to hook up a computer, bring up the application that runs the PLC and single step with a computer. What they did on the Amatro line is they set up a single step function. So you can literally step each one of those stations and see exactly what happens on each program step inside the PLC. If we want to see what path it'll follow, then we'll go into teach run. So this allows us to run the program, but you still have your hand on that dead man switch, right? You understand? So if something happens, you can still let go of it, right? You understand that? The speed on the Motoman and the FANUC, the speed is limited to 250 millimeters per second if you do teach run. On the KUKA and the ABB and the 430 IW over there, they have what they call a high-speed teach. A high-speed teach has nothing to do with jogging the robot. What it deals with is when you run the program. So if you've got a high-speed teach capability, you're going to have to be careful because this will run the the program at production speed. So you don't be around the robot because it's going to be moving real fast. Well, depends on the actual program itself. Automatic mode, we can run it in single step. And we run it in single step, or we can run it in play run, or automatic run, whichever one you're going to call it. This is when it's going to run the program from start to finish. Everybody okay? Each single step robot performs one move instruction at a time. Some of your robots skip over non and move instructions. This might become important if you put an instruction in there to cause it to open and close the gripper, which means if the gripper don't open because the single step skipped over that, then you could collide the gripper or something with something, right? Each pendant must be activated. You have to press to make each move. You got to have the 3 position enabler in play. And the robot may not follow in single step mode. The robot will not follow the same path when the program's written. So normally what we use single step for is to verify our instructions and to verify our points. To make sure I meant for the robot to come down and all of a sudden it takes off up in the air, right? Which means I taught a point wrong. And we use to verify positions of the robot. So normally this would be the step that when we write a program. The first time we would do it is we would run single step teach, right? You'll understand that. That would be the first thing through the program. If all your points check out and it moves in the right direction, then you'll run it in single step. You'll run it in teach run, but you'll run it at a real low speed, right? Does that make sense? And then you'll increase the speed up in teach run until you okay with the way it moves, and then you'll do what? Then you'll switch it over to auto. That makes sense? And then usually we run it auto single step, and then finally we run it into run. And that way you're going to have very little chance of having a collision. Teach run mode. The robot will execute the program from start to finish. Teach pendant controls will have to be activated, pressed, or moved and held in place during the program execution. Teach, the maximum move speed will be limited to 250 millimeters per second unless you have high-speed teach selected. Now, the problem we have with the KUKA is a lot of our we're going to tell you to set it at 10%. Most of your robots, it's going to be 10% of the program speed up to 250 millimeters per second. The KUKA, if you put it on teach, and you have your low speed teach, it's going to be a percentage of 250 millimeters per second. So that means if your program calls for a 100 millimeter per second move, then it's going to be moving extremely slow. So if you're on the KUKA, which nobody in here is, normally we use high speed teach, so it moves at a percentage, but you really have to pay attention to your speeds. So high speed teach is available on the ABB and the KUKA and the Big FANUC, but nobody uses the Big FANUC in this class. So we went over their last class and we actually let y'all see that Big FANUC run. That was high speed teach. So that was actually the speed of the program. Do not set the pendant speed above. Ooh, this is 100%. Look at the lab. The lab tells you how fast we're going to do the percentage. Automatic mode, single step and run. Work self safeguards must be in place before the controller is allowed to move the robot. So what does that mean? You got to button the cell up, right? You got to close the doors, right? You'll understand that. So none of these robots will run if you switch it out into automatic mode. Teach mode isn't, the intent is for you to be able to get into the work cell with the robot. Huh? They're not active, which makes sense. You know, that would be like, you know, you're trying to work on a car and you got to stay outside the cell. If you're going to work on a car, you got to be what? You got to be in there with it, right? You understand? You might have it jacked up. You might have the engine running, but you got to be in there. You know. Single step button. So we got single step buttons on the teach pendant or controller must be pressed to cause the program to step to the next instruction. Round offs do not come into play. Play run, robot moves at the speed specified in the instructions times the % set on the teach pendant. The 250 millimeters per second speed limit no longer applies. But we can still control the speed, but we're going to set a % of the program speed. Controller runs the program from start to finish. So this is the mode we use to actually finally run our programs, right? But it takes a little while to get through and make sure everything's right. So round off, FANUC calls theirs what? Continuous and fine. Continuous means we're going to use round off. Fine means we're going to hit the point. So Motorman calls theirs a what? If we don't specify a round off, it's going to be calculated according to the speed. It's not specified in the program. So the Motorman will automatically round off if you don't tell it to do something different. KUKA calls theirs a CDC data. I need to check that. I think it's wrong. ABB calls theirs a what? A zone. And I think some of y'all in this class we're using the ABB, the Motorman, and the small man. I don't know which one y'all was on. I can't remember. Are we okay? So we'll go over there and look at some round off and let y'all see that. Let y'all look at a program. We're going to do this on the FANUC robot. I'll single step the program, and then we'll look at the procedure we would go to write. We'll look at the program. It's a very simple program using nothing but joint moves.